And welcome, calculus folks, for round 2 of related rates. Here we go. Um, Another typical problem. A space shuttle is launched vertically and blah, 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 blah. You're reading this. Um, let's draw a diagram. The diagram looks like the space shuttle. Here's the space shuttle. Nice. It's launched vertically, right? There, and there's the space shuttle after it's been launched vertically for a little bit. And it's being tracked by a radar station, which is located on the ground 3 kilometers from the launch site. So that's 3 kilometers. And there's the track. What is the vertical speed of the shuttle at the instant when its distance from the radar station is 5 kilometers, and this distance is increasing at a rate of 5,000 kilometers per hour? All right, a lot of information there. Let's there's two things going on here, right? There's a distance, and then there's also a speed, right? Increasing at a rate of 5,000 kilometers per hour. So this here is actually changing, right? So what am I going to call that? Maybe I'll call it the S for I don't know, not because I don't want to use R because R would be rate. I'm going to use I could use no, I don't want to use H because H is the height. I'm going to use S. So I'm going to call this ds dt, and that is 5,000 kilometers per hour. So this distance is increasing at 5,000 kilometers per hour. Um, okay, great. What's required? We want to find what is the vertical speed of the shuttle. Well, I said this is the height. We want dh dt when this distance is 5. So we could say that we have this to be s equals 5, right? But actually, once we have 5, we can actually calculate what h is too, right? This is just Pythagorean theorem. This is part of my analysis step, I guess, over here, and I'm already sort of thinking out loud. Uh, it's 4, isn't it? This is a 3, one of the famous math teacher um, triangles, Pythagorean theorem. H is 4. Okay. Um, if I want to find dh dt, how do I actually do that? Well, I'm going to write down an equation that relates the variables that are involved. I'm going to relate s is equal to h squared plus 3 squared, right? That's not changing. That's 9. And then I'm actually going to take the derivative of this rather than solving for s or something silly like that. I'm going to take the derivative of this implicitly. So I take the derivative of the left side, that's 2s, and then the derivative of the inside, 2 ds dt. Right? And then the derivative of this is 2h, and then dh dt. We get a little smile there because we know we want to find dh dt. And then the derivative of the 9 is just 0. Notice the 2's cancel out. Bing, bing, cancel out. That's the sound of something canceling out. Bing. 1, 1. And now what do we have? Well, we have s is 5. ds dt is given, 5,000. The height we calculated was 4. And then there's what I want to find. This is no problem at all. As long as I set up the formula and carefully take the derivative, these questions feel like they're a lot easier than the optimization questions, and I would argue they are. We'll see some a challenging one coming up. DHCP is 62,500 kilometers per hour, and this is all the solution here somewhere. Where does the solution start? In here somewhere the solution starts. And I know if you're not writing the GRASS, I don't care too much about that, but you need to show some setup steps, right? The shuttle speed is blah, 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 blah. You finish off the statement. Dandy, let's go on to example 2. Little Mr. Restall loses interest after we've solved the question. Okay. Oh, this is a good one. This was a hard optimization one. This one, though, notice is a little different. We're not interested in how close, like what's the minimum distance that the ships get. We just want to know at what rate are the ships separating or approaching when B is exactly southeast. So it is challenging because there's two things going on. There are distances involved and there are velocities involved. So let's try and carefully draw a diagram. Here's ship A sailing south, and I don't want to make this too long because I don't know what else is going on in the diagram. This is 16 kilometers per hour. That's a rate, right? That's some sort of rate. B, which is sailing, is due north. So ship A is due north of a second ship. So there's the second ship, B, and it's due north. It looks like A is sailing straight towards B, but B's taken off. It's going east at 12 kilometers per hour. Okay, and we want to know at what rate are the ships separating or approaching? Well, let's see. There's a distance between the two ships, right? And last week or last couple classes, we were talking about the minimum distance there. But we want to actually calculate, I'm going to call that R for some reason. We want to calculate the rate, right? What's required here is dr dt when B is exactly southeast. When B is exactly southeast. So what it's saying is we want to have this set up when this and this are exactly at 45-degree angles to each other, right? So I'm going to draw in a different color this snapshot that we want to find. So here's this is a distance snapshot, right? It's always changing, but this is the distance snapshot, right? A and B, right? A has moved from its initial position, and B has moved from its initial position, and now B is exactly southeast of A, right? So that means that we have, this is 45, and this is 45 degrees. Okay, well, notice that we don't know any of the distances at all. No distances. No distances at all. We have no idea. And so, how do I handle this? Well, I know that this is R, right? But if I call this distance, and I don't know what it is, X, then this is also X, isn't it? So this R then is just root 2x, because this is a 1, 1, root 2 triangle. And now I think I've got enough tools to actually try and set up a formula and take the derivative. Again, I'm not quite sure when this is. So this is when this happens. And I'm not going to fill that in. I'm going to do some work here and see if we could figure it out. Well, what's the formula? Hopefully you see a Pythagorean theorem here, right? The Pythagorean theorem. This is a Pythagorean theorem where if I call this x, or no, I'm not going to call this x. I'm going to call this distance. Let me call this distance a, and this distance b. Then I have a squared plus b squared equals r squared. And we want this special r where r is the square root of 2x. That's what we want to have happen. Okay? That's what we want to have happen. Okay, so what's the next step? Even though I'm a little bit nervous about proceeding here, I think I'm going to try and take a derivative. I'm going to try and take a derivative and see what we can fill in. See what we can fill in. So take the derivative here. A and B are both changing. They're both functions of t. So all of these are like a triple chain rule here. So this is 2a dA dt. And I have 2b dB dt. And 2r dr dt. Okay, there's the little smile. We get a little smile because that's what we want to find. And I get a little smile because the 2's cancel. Bing, bing, and bing. All right, great. And actually, what else is nice here is for the snapshot in time, these A's and B's are distances, right? What is the distance that I'm interested in? I'm interested in this distance being x, this distance being x, and this distance being the square root of 2x. This is when this southeast thing happens. So here I have the value a is whatever distance it is. Oh, I don't know what it is. I'm calling it x. B is the same distance to get it to be southeast. And then I calculated the radius then is the square root of 2 times that distance. Whatever it happens to be, we weren't given in the question, but it turns out we don't really care because watch what happens. This x is some distance, but if I have one here, and I'm going to be careful here, and put that one in the square root of 2x, this is what we want to find over here. What it's going to be is that it's going to appear in each term. This x is going to appear in each term, and I will be able to cancel it. I'm worried about what's dA dt and what's dB dt. I got to figure that out. dA dt. dA, well, what's the rate that A is changing? If this is A in here, it's shrinking, right? Because A is getting smaller by the hour by 16 kilometers per hour, right? dA dt is negative 16. And what's dB dt? Well, it was 0, and then it grew, and it's growing by 12 kilometers per hour, right? So dB dt is 12. dA dt is negative 16. dB dt is 12. I could collect those like terms now. Negative 16x and 12x is negative 4x. And well, what's the x? What's going on with the x? As long as x isn't 0, and x isn't 0 because, well, I guess we could have started with the ships right on top of each other, but that seems a little bit strange to think about that. As long as x isn't 0, we can bing those away as well. And so what do I got? I have my answer falls out almost immediately here. Just divide by the square root of 2. And my dr dt is this value, which is about negative 2.83. And that's kilometers per hour. So what does that mean? Are the ships getting further apart or getting closer together? Well, since that r is shrinking, decreasing, minus by 2.8, they're getting closer. Solution starts up here somewhere. The ships are approaching each other at 2.83 kilometers per hour when B is southeast of A. Nice. Okay, I'm going to pick up the last related rates question of the chapter, actually the last question of the chapter, the entire unit, here in part 2.